Here's video number 2 for the chapter 2 review. Number 3, it says write an equation for the line tangent. So as soon as you see write an equation, and we know that it's a line, we're going to have y equals mx plus b. Remember that m is your slope, and the way that you find a slope is through the derivative. So that's where we're going to start. The derivative of y is equal to 8x plus 0, or minus 0, however you want to look at it. Now if I evaluate it at the x value of that point, then my slope is negative 8. There's a couple ways you can go about finding the line. My preferred method is point slope. Some people prefer slope intercept. Point slope says y minus y1 equals m times x minus x1. It's found in chapter P. If you want it explained a little bit further, you're going to substitute out x1, y1 with the point, and you're going to substitute out the m with the slope. When you plug in a negative number, it ends up being positive because it's a double negative. And at this point, solve for y and you'll be done. So if you graphed this point, you would see that on that parabola, at that point, this line would be tangent. I won't do this with all of our examples, but let's just look at this one to be sure. So the original equation was 4x squared minus 9. Then we've got the tangent line, negative 8x minus 13. I'm going to graph them both. And then we're going to trace, no, we're not going to trace, we're just going to go left or right. Let me go to negative 1 up to negative 5. So right about there. Now would you agree that this line hits the original function at that point? And I hope that you would. I'm sorry for the lighting. It's a dark day outside, so we're not getting a lot of natural light. Hopefully you can see this without a problem. Our 6 trig derivatives, we've got derivative of sine is cosine x. Derivative of cosine x is negative sine x. The derivative of tan is secant squared x. By the way, that's also the same as saying secant x quantity squared. They mean the same. Oh, I'm not even on a page. They mean the same thing. Cosecant is negative cosecant x cotan x. Secant is secant x tan x. It's important to have the angles attached to each of the individual functions. And then cotan is negative cosecant squared x, or negative on the outside cosecant x squared. They mean the same thing. It says, besides memorization, what helpful hints can you think of that will remind you of the 6 basic trig derivatives? Well, what I'm noticing, every single one of the co-functions, cosine, cosecant, cotan, all have negatives. So that's something to remember. When you take the derivative of a co-function, you have a negative answer. Something else to remember, the brother-sister combinations, if you will, have very similar responses. I would pair sine and cosine in a family together. I would pair secant and cosecant together, and you see that those are behaving very similarly. And then tan and cotan have very similar derivatives as well. When you do a rate of change equation, your variable is always t. Anytime you talk about rates, you're talking about a change of time, or these things changing over time. It says, what is the difference between average velocity and instantaneous velocity? Average velocity would be like any average. If you wanted to take an average velocity, you'd take your beginning, never mind, I won't do it that way. Your beginning distance, so we'll say S2 minus S1, displacement, distance, it doesn't matter what you're using for that, T2 minus T1. Let me explain this further. If it's average velocity, you know that you're going to have meters per second, or feet per second, or meters per minute, or miles per hour. So your distance is over your time. To get an average velocity, you take your start and finish distance and times and find their slope. Instantaneous velocity is the derivative of the displacement or the distance function. And we're able to plug in a very specific time into that function to get a very specific velocity. These are not the same. This one is done with formulas prior to calculus. This is in need of a calculus formula. So we're going to start with number 4. A silver dollar is dropped. First of all, if it's dropped, there is no initial velocity. You only have initial velocity if it's thrown or tossed. It's dropped off a building, 1362 feet tall. Determine the position function. The position function is always of the form, now since this is feet, we have to remember acceleration due to gravity in feet is negative 32 feet per second squared. So that will lead us, and I'll explain why in later chapters, but that will lead us to this formula. V naught and S naught are initial velocity and initial displacement, initial distance, initial height, if you will. So if I plug in specifics for this formula, I know that my initial height is 1362, and I know that there is no initial velocity. So my position function is S of t equals negative 16t squared plus 1362. The velocity function, if you remember up here, velocity is the derivative of displacement. So velocity is equal to negative 32t using the power rule. Determine the average velocity. Average velocity is found up here. Now in order to do that, I need to know what, these are times, okay? So I need to know what distance these times are paired with. If I plug in 1 into my position function, I'm going to get 1362 minus 16. 1346. If I plug in 2, I get 1362 minus 64. So average velocity is going to be distance 2 minus distance 1, whoops, that should be a 4, over time 2 minus time 1. It doesn't matter what order you choose, but if you start with the 1346, you'd have to start with the 1 below it. Our numerator is negative 48, our denominator is 1, which means that we are traveling on average negative 48 feet per second. The instantaneous velocity at 1 would be like plugging 1 into that formula that we had above. Negative 32 times 1 means that after 1 second we're traveling 32 feet per second downward. Remember, this is a dropped coin. At 2 seconds, I would imagine that this would be going faster. It's building momentum as it goes. Okay, neither of these is 48, but you can see how as time goes on, there is an average somewhere between these two particular instantaneous velocities that matches the average up here. Find the time required for the coin to reach the ground. There's a clue when it says ground level. If you're on the ground, then your height is 0. So basically we're saying 0 goes in for our function and we need to solve the quadratic, the original quadratic. Because this is an incomplete quadratic, which means the middle term is missing, you can solve this either with the quadratic formula, by factoring, or by using just manipulating the equation and getting the t by itself. That's what I'm going to do. I'm going to move the 16 over where it becomes positive. I'm going to divide both sides by 16. I get 85.125, and then I'm going to square root both sides. Now remember, when you take the square root, both positive and negative are answers. However, if we're talking about time, you don't have to remember the negative number because we don't work with negative time. So the square root of that response is approximately 9.2. And I'm going to change this equal to approximately equal 9.2 seconds. Normally in a question like this, in a testing situation, I would tell you round to the nearest whatever. However, if I don't, just use your judgment. Find the velocity at impact. Well, at impact, remember, we have a height of 0, and it takes us 9.2 seconds to get there. So if this is a specific velocity, we're using this function. We need to know time. So what's the time? 9.2 seconds. I guess these are approximated too because I'm using an approximated number to begin with, or approximate number to begin with. But for right now, I'm not going to worry about that. Negative 294.4. So if this is in the air that long, it's going to be moving awfully fast once it gets down to the ground, or right before it hits the ground. See if that makes sense. 1362, that is awfully tall. You're talking about like a very tall building. So would it make sense that it would be moving that quickly at the bottom? And I do believe that makes perfect sense. Now we've got a ball being thrown. So if you remember, the position function is always of this form in calculus. We use the standard numbers. We don't use metric in calculus, rarely. You might have a specific question that uses metric, but just in general, we're using standard. So this is always going to be the case for position. Now figure out where everything goes. It's thrown at a velocity of 22 feet per second, negative 22 feet. Okay. So here's what I know so far. Straight down from the top of a building. Okay, so this building is 220 feet tall. That's our initial velocity, or our initial height. Because it's up in the air, it's a positive number. What's the velocity after 3 seconds? So what are they asking here? Velocity as it relates to displacement is the derivative. After 3 seconds means you're plugging in 3. Negative 118. Now, I did this whole problem without reading. Okay, we don't want to know, oh, we do want to know 3 seconds, but we also have another piece here. I apologize. What is its velocity after falling 108 feet? So 108 feet would be its new height. I'm going to bring this over. Let's see. 112. I could solve this. I'm going to just use the quadratic formula off to the side here. And actually, I don't know if you've ever done this, but I'm going to store negative 16 into A, negative 22 into B, and 112 into C. And then I'm just going to type my quadratic formula. negative b plus, now I can't do plus and minus at the same time, so plus right now, square root of b squared minus 4ac all over 2a. That's a negative number. Remember, that's time, so I don't want that. What happens when I change that to the minus, and I get about 2 seconds. That's what I'm going to use for my time. So now plug in 2, and maybe for a more accurate answer I'll use 2.05. It really doesn't matter at this point. Negative 87.6 feet per second. So we're not all the way down to the ground yet. It would make sense that we would be going a little bit slower than when we finally get there. Or not a little bit slower when we finally get there, but slower than almost a second later. Product rule, if you think of the product being f of x times g of x, then the product rule is the first times the derivative of the second plus the second, remember plus and product, times the derivative of the first. Quotient, if I put g of x below, then this is the denominator, always start with the denominator, times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. When you do these for your assessment questions, it is not necessary for you to simplify, just do the rule. If it's a nice simplifying, go ahead, take it that extra step, but I don't want you to focus all of your attention and time on that. Number 6 is a product. I know that because I have something that I would call an algebraic expression here, meaning it's just a basic calculator algebraic rule, I guess, followed by a trig function. 2 separate functions. When one stops, the other one starts. Those are my 2 functions I'm going to use for my product rule. Therefore, the derivative of f, and our variable in this case is theta. Now before I continue, I want you to see this as 5 theta plus 1 to the 1/2 power. You should always rewrite your formulas so that you're working with exponents if it lends itself to that. Alright, so we've got the first times the derivative of the second. The derivative of cosecant is negative cosecant theta cotan theta plus the second times the derivative of the first. Whenever I use the chain rule, I tend to always use brackets. That's just my preference. 1/2 comes down, 5 theta plus 1 to the negative 1/2 times what's inside. Okay. We've got a quotient rule here at the bottom. The derivative of h with respect to x is going to be the denominator times the derivative of the numerator. The derivative of 9 plus 3x is just 3 minus the numerator, because it's a binomial, I have to put it in parentheses, times the derivative of the denominator, which is derivative of cosine is negative sine. Alright, so I'm going to put the negative with the 6 here, times the derivative of the inside function, all over the denominator squared. Now, if by chance you saw cosine 4x in each of the different terms, the beginning, the end of the numerator, and at the bottom, I'd start canceling some things here, but I don't see it in this section. Therefore, I'm not going to simplify any further. You could bring the 3 with the 6 and make an 18. You could distribute here if you wanted, or put the 4 with the negative 6. That's fine as well. Make sure that there's either a bracket or a parenthesis. Otherwise, this would look like a minus 6 sine 4x times 4, and that would not be correct. What's the process necessary for finding the fifth derivative? Simple. If you have a function To find the fifth derivative, you have to first find y1. Then you have to find the second derivative. Then you have to find the third derivative. Then you have to find the fourth derivative. It's not until then that you can find the fifth derivative. Okay? Each of these is required to do the next. You can't jump from one to the other without going through every successive number in the meantime. We're up to lesson 2.4. First thing with chain rule is to make sure that you see it as an inside-outside function. And remember, rewrite anything that can be written as an exponent. If the number's on the outside, it is the root of the exponent. Okay? The derivative of this function is the outside derivative, which is the 1/5, times the derivative of what's inside. Well, I'm going to leave the 15 minus 3x cubed in here, and then now take its derivative, which would be negative 9x squared. Could simplify that further. I'm not going to worry about it right now. This one is very complicated, but it's extremely important that you understand. I'm going to rewrite it as cosine. And remember, if this is cosine cubed, it means the cosine function is cubed. Cosine of what? Cosine of secant of 5x to the fourth plus 10. This parenthesis needs a second. This parenthesis needs a second. And it's the cosine that's cubed. Follow these parentheses to know what part you are in the journey. First derivative I'm going to take is the cube derivative, which means I take 3, bring it down, and then raise it squared. Nothing changes on the inside. So that derivative is complete. Now the second piece is what's inside these parentheses, which is cosine. The derivative of cosine is negative sine. Negative sine of what? Of what cosine was. Don't change any of it. Make sure that your number of parentheses match. Alright, took the derivative of cosine. Times what? Well, the next thing listed is secant. The derivative of secant is secant tan. Secant tan of what? Well, secant tan of what secant was of. Alright, so we've taken that derivative. Now the only thing left is the derivative of what's inside. This is a complicated piece, so I'm going to put it together in its own set of brackets. And I'm going to multiply by 20x cubed. So there's the first, there's the second piece, there's the third piece, there's the fourth. All four pieces come together to make the derivative of that complicated composite function. Implicit differentiation is much like the chain rule, except instead of having that complicated function on the inside, you have a substituted value of y. Okay. Before I begin this process, I want to analyze if there's any product rule, the product rule or quotient rule that might come up that I need to be aware of. X squared has no problem, nothing attached to it that should bother me. But because I see a combination of x's and y's here, I know that they are separate functions. I like to put a box around them, and I'm going to separate the box where I change from one variable to the next. Those are my two functions. Y cubed is fine, 10 is fine. Derivative of x squared is 2x. Now I've got the product rule. It's the first times the derivative of the second. Well, y squared is 2y to the first. But because y is a hidden function, you always have to tag on y prime when you take its derivative. Plus the second. Don't forget where we were in the product rule. Times the derivative of the first. The derivative of y cubed is 3y squared, but we just differentiated a y, which means we tag on y prime. and the derivative of 10 is 0. Your derivative is correct, and for the most part you have a good chunk of your points at this point. But clean it up. And everything that has a y prime on it is going to remain on the left, and everything that doesn't have a y prime is going to move to the right. These values are commutative because addition is commutative. It really doesn't matter as long as you keep the sign with the function. So as I pull out the matching y prime, greatest common factor, I'm going to rewrite it starting with 3y squared minus 6xy. That's just my own personal preference. And I'm going to rewrite this one as 3y squared minus 2x. Y prime is the answer you get when you take 3y squared minus 2x and divide by what it was attached to. I feel like it's very important to say at this point, you cannot divide the 3y squareds. They don't match. Well, they do match, but because they're part of polynomials, because they're part of, in this case, binomials, you can't take a piece of the binomial apart. The binomial is fused, if you want to think about it that way. Same thing here. Derivative of y squared is 2y, but we took the derivative of y, so tag on y prime. And then hopefully you recognize this as the quotient rule. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Now in order to solve for y prime, all you have to do is bring down the 2y. This may or may not simplify to something nice. I'm not worrying about it right now. Okay, as far as I'm concerned, that's okay for the time being. Now, if you have a 2 here, a 2 here, and a 2 here, I can cancel everything by 2. And in fact, I probably should, but to save time, I'm just going to stop at this point. A couple formulas you need to know for unit or section 2.6. Some formulas that come up: Pythagorean theorem, a squared plus b squared equals c squared. Area of a parallelogram is length times width, or base times height. Area of a triangle is half of that. Area of a trapezoid is 1/2 times the sum of the bases times h. Area of a circle is pi r squared. Your trig relationships, that's your SOHCAHTOA. Up at the top, volume of a cube. If you remember that a cube, all the sides are the same, then the volume of a cube is just whatever that side is, whoops, cubed. Volume is 3-dimensional. You could use any variable you want there, but I just figured I'd be consistent. Rectangular prism. You most recognize it as length times width times height. Volume of a cylinder is pi r squared h. It's just a circle with a depth to it. Volume of a cone is 1/3 the size of a cylinder. Volume of a sphere is 4/3 pi r cubed. And in terms of other, anything you can brainstorm that you might think is important would be helpful here. Okay, I took the liberty to draw some of these already, but we're going to hopefully truck through the last 6 questions pretty quickly. Water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 4 centimeters per minute. So the way I read that, the way I read that, the rate means it's got a dt in it, and because it's radius, then I'm talking about dr dt is 4 centimeters per minute. It increases, that's why I'm using a positive number. How fast is the area? That's telling you what you're going to take the derivative of. How fast is the area of the pool increasing when the radius is 5. Area of a circle is pi r squared, so we take the liberty of taking the derivative of this, everything with respect to t. There's only one variable on this side, pi and 2 are both constants. If I bring the 2 down, I get 2 pi r dr dt. You will attach whatever dt to any of the variables that you're taking the derivative of. Then plug in what you don't, or what you do know. I'm trying to find dA dt. My radius at this point is 5. My rate that the radius is increasing over time is 4. So when all is said and done, this is 40 pi centimeters per minute. That's your exact answer. It is approximately equal to 125.66 centimeters per minute. Okay. Oil spilling. It's an area again, but let's read through this. Oil spilling from a ruptured tanker spreads in a circle on the surface of the ocean. The area of the spill increases at a rate of 9 pi meter squared per minute. Now this is, this portion right here is given to you. How fast is the radius of the spill increasing? Now we're looking for dr dt when we're given dA dt. A good way to, or a good clue is to look at the label. Since that's squared per time, it's area dt. So I'm not going to rewrite the whole formula. I'm just going to rewrite what it came out to be. dA dt equals 2 pi r dr dt. My area is 9 pi. My radius is 10 meters. Make sure that your labels are in the same family. If we have centimeters and meters, we'd have to do some conversions. We're solving for dr dt. The right side of the formula becomes 20 pi dr dt. And if I want to solve for dr dt, I get 9 pi over 20 pi. And that simplifies to 9 over 20. Remember, we're talking about radius, which is measured in meters, over time, which is measured in minutes. This is the exact answer. However, the approximate answer, I guess it wouldn't be approximate unless this doesn't come out nicely. It comes out nicely, so 0.45. Okay. Now we've got a cone, it's being filled. We're told that the radius and the height are the same values. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. Water level rises. Water rising would be h. So this is dH dt. At what rate is the water being poured into the cup? When you pour water in, you're talking about dV dt, and the water level is 8. I didn't mean to write 8 again. I meant to write that it's your height. So we're using the volume of a cylinder formula. Because it's a cylinder, it has 1/3. But I do want to point out a couple things. Well, I will when I get there. We've got two variables. So when I take the derivative, I'm going to have to use the product rule. I'm going to put all of this together in the first, and this is the second function. The first, just combining pi and 1/3, the first times the derivative of the second plus the second times the derivative of the first. And now let's plug in the answers, or plug in the values we know. We know that the water level is 8. That's your height. Okay, we know it's rising at 2. Rising would be your height over here. What else do we know? Well, we're missing all of this information about r. Keep in mind though, your radius and your height were the same. Radius and height are the same. So they have a 1-to-1 relationship, which means your height and your radius are the same value. My r is also 8, and my dr dt would be changing at the same rate as this. This is not drawn to scale, but imagine an xy equation where the x's and the y's change at the same value, the same rate. So simplify what we have. 64 times 2 is 128. This becomes 64 times 4, 256. I knew that. They both have pi over 3, so I can put them together as 384. 384 is divisible by 3. I think it's 128. Yep. So my exact answer is 128 pi centimeters cubed per second. If you want an approximate answer, 128 pi comes out to be approximately 402.12 centimeters cubed per second. Okay. Last 3 questions. Spherical balloon. How fast is the volume? So volume of a sphere is how I'm going to start this problem. Derivative of that. There's only one variable here, so I bring the 3 down. 4/3 times 3 pi r squared dr dt. 3's cancel. A spherical balloon is inflated so that the radius increases at a rate. Radius rate, that's your dr dt, is 2 over r. It's kind of a vague answer. I don't like when it's a variable, but we can figure this out regardless. How fast is the volume of the balloon increasing when the radius is 4? Just simplify what we have. This is 16 times 4 is 64 times 2 is 128. 128 pi over r centimeters cubed per second. I'm going to leave it like this and just say that no matter what we chose as an r, so in this case r would be 4. I guess I can plug that in. 128 divided by 4, 32 pi centimeters cubed per second. So at that point, it's 32 pi centimeters cubed per second. We've got lampposts. Now, this one right here is non-traditional. I'm going to go over it, but it's very unlikely that you'll see a question this complicated. It's not really complicated, but the setup might take some thinking. A 7-foot person walking away from a 20-foot lamppost. So the person is walking to this point at a rate of 5 feet per second. Since they're walking in this direction, I'm going to call that a change in x. Assume the scenario can be modeled with right triangles. There's a right triangle, there's a right triangle. At what rate is the length of the person's shadow changing? Well, where's the person's shadow? It's over here. Now, this is already determined to be my x value, so I'm just going to pick a different variable for here, maybe y. If I'm talking about the rate that the shadow is changing, that's going to be dy dt. What do we know about similar triangles? Well, the large vertical is to the large horizontal, as the small vertical is to the small horizontal. Do some cross multiplying. Do some combining of like terms. Do some differentiating. I know that dx dt is 5, and that's allowing me to figure out it's allowing me to figure out my value here for dy dt. Had a little brain fart. So dy dt is equal to 7 over 13 times 5. 35 divided by 13 would be the exact answer. Feet per second. But it's approximately equal to 2.69 feet per second. Now I had a brain fart because I saw this 16 feet from the lamppost. It says at what rate though, so we're not actually figuring out anything where the 16 feet really matters because that didn't come into play here. We didn't actually need x in our solving. Last question, an observer stands 700 feet away from the launch pad. The rocket blasts off at 900 feet. Rocket goes up this way, 900 feet per second. Assume the scenario modeled by a right triangle. How fast is the observer to rocket distance? I called this S. It's a distance. Here's the observer. So we're looking for ds dt. Since we're talking about the sides of a triangle, I'm going to use the Pythagorean theorem. Well, my sides, 700 is consistent. That's not going to change. We'll call this y. Okay? It's changing because the rocket is going upward. And then our distance from the rocket to us is s. This becomes 490,000. You take the derivative, it becomes 0. 2y dy dt and 2s ds dt. Well, what do we know? The y value we're talking about is 2400. The value at which we're increasing is 900. Our distance is unknown for a second, and I'll explain that here in a minute. And then ds dt is what we're trying to solve for. It's unknown for a second, but if you look, we have two sides of a right triangle. That means that I can easily figure out the third side, the hypotenuse, using the Pythagorean theorem. Now I'm going to cheat. This is a Pythagorean triple. I know 7, 24, 25. You can do the Pythagorean theorem, you'll get the same answer, but if it's 700, 2400, then this answer is going to be 2500. 4800 times 900 is 4320000, and it equals 5000 ds dt. If I divide by 5000, I get 864 feet per second ds dt. And it's a positive number. Does a positive number make sense? It says how fast is the observer to rocket distance changing? It is increasing as the rocket goes up. That s is getting longer. So yes, that would make sense that that's a positive number. Again, just like before, if you have any questions, you can ask Miss Ali or myself. You know how to get a hold of us, and I'll be uploading this here shortly. Thanks.